What's up, everybody? Welcome back to another video from the Mathnasium. I got a couple questions for you today. First, you got to guess my age. If people were guessing my age, people are going to shout out numbers. However, only one of the answers will be true, right? There's only one solution to what my age is. However, if I asked Antonio Banderas to do as many push-ups as he possibly could, we would be able to say that, Antonio Banderas can do at most a certain number. Now, if he can do at most, let's say 30 push-ups, then how many push-ups can Antonio Banderas do has many different possible solutions. It has a whole range of solutions. And so what we're going to talk about today is we're going to talk about how do we express, what are the different ways that we can express a range of values in algebra. And then we're going to use that skill to talk about different things that we can measure and we can describe in a graph, okay? Or in a function. So let's go ahead and start things off by first talking about that and kind of recalling how we do that. Just a quick refresher. Let's make sure we're good here. We got a pen. Let's think about, whoops. And, we're black, we're good. Let's think about 2x minus 6. 2x minus 6 is an equation. Equations have one solution. And to solve, we would add 6 to both sides. So we end up with 2x equals 6, x equals 3. There is only one number that makes this equation true. But if I change this to an inequality, like 2x minus 6 is greater than or equal to 0, well then, whoa, this is a different ballgame. However, the process for solving it looks similar. The process for inequalities is almost the same as solving for equations. There's with a couple extra little rules, but it turns out we won't see those in this solution. So we add 6 to both sides, we divide by 2, and we get a whole range of values. All of the numbers that are greater than or equal to 3 are solutions. So 3 is a solution, 3.5 is a solution, 4 is a solution, 100 is a solution. There are a bunch of numbers that make this inequality true. So how do we describe those? Well, there's a couple ways. The first way you can describe them is with an inequality. Inequalities describe a range of values. That's one way. Another way you can do it is with a graph. So remember, we can come down here and we can say, all right, let's check this out. We put our boundary in the middle, which is 3. Normally, I would say put 2 numbers on either side. I'm just going to put 1 number on either side to save time for the notes. And if we want a graph on here, we want to talk about the numbers that are bigger, greater than or equal to 3. Well, we would put for less than or equal to, greater than or equal to, less than or equal to, we use a closed circle. So closed circle is one that is filled in. So we fill in this direction, and then we're going to shade the side of the side of my number line that makes this true. Well, those are all the numbers that are greater than 3, which is this direction. Put a little light. There's a third way that you can use to describe a range of values, and it's called interval notation. Now, interval notation always looks like a lower value, comma, and then some higher value. So you have a lower value, comma, and then some higher value. And it is really the lower bound, so it's the lowest possible point you can go to, and then up to the highest possible point you can go to. And anytime you're describing a closed circle as an endpoint, we always use a bracket, and I'll show you some examples of this. Anytime we're describing a closed circle, we use a bracket. Okay, so we always start with our lower bound, the lower bound for the shaded area. So the lowest possible spot we could go is 3, all the way up to the highest possible spot. Well, where does this arrow go? It continues on forever. It's heading off towards infinity. So we can go from 3 to infinity. Since this is a closed circle, right? Closed circles are associated with the square bracket. We're headed off toward infinity there. Anytime we have infinity, well, infinity is something that you can never get to. It's not included in our solution set because it's not necessarily a destination. It's more of a direction. Since you can never get to infinity, we actually use parentheses, and I'll get to that in just a second. So basically, the square bracket and the closed circle, these indicate things that are included in the set of numbers, things that are included. Let's look at another example. What if I wanted to do x is greater than 3? X is greater than 3. If I were to talk about that on the graph, well, that would be from everything. This process is pretty much the same, except instead with less than or greater than, we use parentheses and an open circle. So I would put an open circle, and then I would shade everything to the right, all the numbers that are bigger than 3. Now, every number up to 3, but not including 3, coming from this direction, is a solution. It's a number bigger than 3, like 3.0000001 is bigger than 3, so it's a solution, but 3 is not a solution. So to indicate that, we don't shade it. We leave this circle open. So open circles. Now, the only way this would be different in interval notation is we would use parentheses, comma, and then infinity, comma. Things that in parentheses typically indicate they indicate numbers that are basically not included in our solution set. Okay? So 3 is a solution, so it's shaded, and we have a bracket. 3 here is not a solution to the inequality. It doesn't make the inequality true. So we leave it open, and we use parentheses in our interval notation. Okay? Super. Let's do some examples. I'm going to power through these. Feel free to pause the video and try a couple at any time. All right, let's get going. That is not black. That is. I'm going to cross. I'm going to do my number line. So let's talk about graphing these inequalities first, and then we'll write them in interval notation. Put our boundary in the middle. 6 over here, 4 over here. Fantastic. And I might just, for the sake of saving time color-wise, I'm going to go through and just create all my graphs really fast. -3, 1 to the right of -3 is -2. -4. For here we have a little bit longer. Goes from 2, 4, 6. I bet you guys can get these. All right, in purple, x is less than 5. We can go back to our, so less than or greater than, we use an open circle and parentheses. Open circle because 5 is not a solution. What are the numbers that are less than 5? The numbers that are less than 5 are all the numbers in this direction. Okay, so what's the lowest possible value in my shaded region? Well, the lowest possible value is the direction that it's heading. That's -infinity, up to the highest possible value, which is 5. Since you can never reach in -infinity, we use parentheses. 5 is an open circle, so we parentheses. Next color. All right, let's do this one again. Easy peasy. We got this, no problem. You guys got this, no problem. Okay, x is greater than or equal to -3. Greater than or equal to, referencing our notes, we use a closed circle, right? So we fill in here, closed circle, and we shade the numbers that make the inequality true. What are the numbers that are greater than or equal to -3? Those are the numbers that are to the right of -3, which is this direction. -2, -1, 0, 4, 5, so on and so forth. 1,000. What's our lower bound, the absolute leftmost we can go to? That is -3. Okay, it's got a closed circle, so we use a bracket, and you head off to infinity. Fantastic. Now, this last inequality is what's called a compound. Oops. This is a compound inequality. So there are two inequalities, both of which have to be satisfied, okay? The first is right here. This is 2 is less than x. 2 is less than x can be rewritten as x is greater than 2. So we're looking for numbers that are greater than 2, but numbers that are also less than or equal to 10, right? So we're looking for numbers that are greater than 2, but less than or equal to 10. So the way that I taught my students to graph these is above the graph. This is our scratch work. We're looking up over here, numbers that are less than or equal to 10, numbers that are greater than 2 going this way. When they're written like this is a compound and inequality, and it really means where do these two things overlap. I think it's a good use of our time to start at the endpoints because we know they overlap in the middle. So it's the endpoints where things get interesting, right? They overlapped at this closed circle, so we can put a closed circle on our line there. And then they overlap at, do they overlap at 2? Well, 2 is, this is not filled in, so they actually don't overlap at this point, which means an open circle comes down. But they do overlap everywhere in between. Now, writing this long compound inequality is a pain. You got to focus on, there's more to write. Writing it as a graph is more work. I think it's easier to just write this interval notation, which is lower bound of 2, lowest value, up the upper or the highest value is 10, and then square bracket, parentheses. So that's how we do interval notation for an inequality. And I think it's the best way for us to represent a range of values. So let's go through and let's remind ourselves of a couple things before we start describing functions. First of which is, remember that the domain is the set of all of the x values. And the range is the set of all y values that are possible for our function, or that our function hits. How do you find these from a table or a set of points? Well, from a table or a set of points, you just write them down. You just list them. When you're looking at a graph, you can identify the domain and range using a couple little tricks. So I always imagined, to find the domain, if this is our function, imagine, this getting squished up against the x-axis, right? It's being squished up again. If you were to press straight down, all of these things would get hit on the x-axis. So to identify the domain, you kind of take the function and you squish it down against the x-axis, and so that's how we can figure out where the domain of our function is. If that doesn't work for you, imagine, you're creating a shadow against the x-axis with a giant flashlight that's being held up above, right? And it's creating a shadow. So you have rays, yeah, and that also works. So that's our domain. And for the range, it's the same thing. You're not pressing it, you're not pressing against the x-axis, you're pressing it against the y-axis. So you're seeing where, if I were to squish this up against the y-axis, where would it hit? If I'm coming directly from this direction, some things get hit by the function twice, right? So if I squish this way, all of these points are going to collapse. They'll hit here and here, so on and so forth. So we're squishing against the y-axis. We're just going to do a ton of examples so that you can see some practice. And we're going to describe the domain and range with interval notation, what we just learned. All right, let's get started. Let's hop to it. So how we list domain and range is you'll say D for domain and then a colon. And you imagine you're taking this item and you're pressing it down, you're squishing it down against the x-axis. So everywhere that the function would hit would be this little line right here. And it turns out that's our domain. We do have to pay attention to the end behavior of the function here. So since these are closed circles, that means that they are included. So our domain goes from -2 up to 1. Closed circles indicate they are square brackets. Our range, we don't look at where it hits the x-axis. We look about pinching it to the y-axis. So you can see that if I were to smush it in on the y-axis, those would be all the numbers. I'm squishing this in like that. Those would be all the numbers that get hit. What's our range? The range goes from 0 up to 3, and we do brackets just like that because the endpoints are closed circles. Super special. Changing colors in purple. You guys can try these on your own if you think you've got it. I bet people could probably have it by now. We do have a couple weird things to talk about here, but that's all right. So if I were to take this and squish this down on the x-axis, squishing it down, it would look like this. All the way over to 2. Those would be all the things on the x-axis that get hit, which is fantastic. Now you got to keep in mind, this endpoint 3, that's an open circle. So we're going from -3 up to 2, pressing against the x-axis. 2 is included because that's a closed circle. -3 is not because it is open. And the range, remember, we're squishing it in towards the y-axis, right? We're pushing it this way and this one this way. So all of our y values are going to be held in between this very narrow area. So we go from, in this case, the lowest possible y value is 1, and the highest possible y value is 2. This one has a closed circle, this one has an open circle, so the lower value still gets the parentheses here. Okay, next one, pressing down against the x-axis. If this were to fall down on the x-axis, that's our domain. Domain lowest value is -2, and that goes up to 1. That open circle, parentheses, closed circle bracket, range. Okay, the range is a little different. So for the range here, you think about, all right, what's the lowest I get in the y direction? The lowest it gets, it kind of turns around right here. And when you see a bend where it turns around in a graph, we kind of just assume that it gets to that point. It's not getting ridiculously close and turning around just before it gets to 1. So we would say we're going from 1 is the lowest possible y value all the way up to 5, both of which in this case are included because I said we always assume that it reaches that number. I'm having fun. Math is fun. Man, I just get so stoked. Heck, in range. All right, let's do some more. You guys try some of these. Maybe it'll bring up some questions, but we'll see. All right, I'm gonna get started. Find the domain and range. Domain and range. Squishing on the x-axis. I'm not going to color the lines this time. The domain here is the lowest possible x value, which is -5. This goes from -5 all the way up to 5. The end is closed, so bracket. And here the range. Assume it's turning around at that point, so the lowest possible y value is -4, highest possible y value is 4, and again, those are both. All right, here we go. Domain. Let's think about this. Squeeze this down onto the x-axis, pressing it down onto the x-axis. The lowest, this goes on forever in this direction. We can assume that it continues both up and over. And it continues up and over. The lowest possible x value here would be -infinity, which is, of course, a parenthesis, something like that. All the way up to 4, which is a square bracket. And the range, and you guys can, if I'm doing a lot of examples, feel free to skip these if you need to see more. There are more here. If you want to watch them all, then you can. Okay, the lowest possible y value is 0. That's the absolute lowest possible y value, and it's going to continue up, and it'll continue up for a very long time. Specifically, it's going to continue up forever. So it'll go all the way up to infinity. Now, it doesn't really, if you ever see like an asymptote or a dotted line that it's approaching, you can assume that it stops. But if it goes up like this, you can assume that it's going on forever. Okay, and now my favorite one. This one is fun. Yay. Okay, domain. Some people are saying, oh, there's a gap right there. Careful. Okay, the domain goes from 1, and there is no gap until the open circle, up at 4 where it stops, because these closed circles actually, the function actually exists. Exists right there. It is part of our domain. So our domain goes from 1 up to 4, parentheses, square bracket, like so. And the range in this case is different, okay? The range, what are all the possible y values? Well, we can't say that it goes from 1 to 3 because the numbers in between are not included. There are gaps. There are gaps between where our solutions are. There are only 3 possible y values. You can list them in a set. You can list them vertically. I'm going to list them in a set. This is not interval notation. This is just saying my 3 possible y values are, the number 1, the number 2, 3. It's not from 1 to 3 because, for example, 2.5 is not included. Remember, this represents everything from 1 to 4. Everything from 1 to 4, not including 4, is part of our domain. These are the only values of our. Okay, I think that I have maybe driven that into the ground. Now let's do something even more fun. Okay, a function is, we say a function is increasing if it, air quotes, goes up. We say it's increasing if it goes in the upward direction. What do I mean by that? Let's draw a pretty picture. Okay, if we go from left to right, if we're biking uphill, we're going up. Okay, so this is an increasing function, going up like this. Now, I can't say that it's positive slope because we've only talked about slope with lines that are straight. Some of these lines that are curved are still increasing, but I don't really want to say positive slope, but it does look like positive slope. A function is decreasing if it goes down. Whoops. If it goes down, air quotes. What I mean by goes down is this, okay? As we go from left to right, it's headed downhill. It might be a curve. It might be, that one wasn't great. Oh, I made the cursor disappear. That's weird. So if it goes down like that or something with a curve, that's fine as well. And a function is said to be constant. Where is my cursor? Hold on, I'm going to pause and try and figure this out. Oh, there we go. Function is said to be constant if it stays flat. And on a graph, what does that look like? That looks like it is horizontal. So this is kind of like slope 0. Clean that up a little bit. My cursor's still being weird. I'm going to try and figure this out. Hold on, I'll be back in a sec. All right, we're back in action. Should be good here. Oops. Hold on. Hold the phone. Make sure I select my purple pen. There we go. Also not working. Pause again. Holy cow, just a sec. All right, 28th time's a charm. Here we go. Coming down like this, it is said to be constant if it stays flat. That means it looks like it has 0 slope. So constant is like, looks like 0 slope. Decreasing is it looks like negative slope. Increasing looks like positive slope. So we're going to say increasing, decreasing, and constant instead of goes up, goes down, stays flat for the rest of the class. But that's how we describe them. Okay, so let's practice finding where a function is increasing, where a function is decreasing, and where a function is constant. So we'll do it with this function first. I'm going to do it in the order of increasing, decreasing, constant. I'm going to represent increasing by the color green. So I'm going to say increasing. Where is my function increasing? Now we are looking here for the x values. We are looking for the x values where it's increasing. So I'm actually going to be shading things on the line. Increasing is like where you're biking uphill. So if I'm riding my bike, I'm biking downhill over here, and then we turn around at the bottom and start biking uphill. So where is this increasing? It's increasing from here all the way off that direction. So that's where it's increasing. It's increasing from -1 off to infinity. Okay, now infinity is going to be parentheses, but what do I do here? Is it increasing right at this little, where it turns around? How can we talk about the slope at a point? That's kind of strange. Turns out that's a question for calculus. So what you need to know in this class, well, yeah, it is. Well, I guess you could kind of talk about it later. But what you need to know for this class is that at this point, you don't need to worry about any time where it turns around like this, where you have a maximum or a minimum, or you have a point where the slope changes on either side, from like positive to negative, is you don't need to talk about that point, or you don't need to include it in either the increasing or the decreasing. So we just leave that as, just a parenthesis. So whenever you're talking about increasing and decreasing, you're going to use parentheses and you won't see square brackets. Okay, let's go to decreasing. Where is our function decreasing? Where are we, if we're going from left to right on our bicycle, where are we riding downhill? We are riding downhill during this whole segment, right? During all of these x values, we're riding downhill, and only when we turn around at -1 do we start riding uphill. So there's our decreasing. We're riding, whoops. Okay. So we are riding, that is from -infinity all the way up to -1. Oh yeah. Lastly, in blue, where is our function constant? Where is our function constant? So if you look through here, is there any spot where it stays flat over a period of time? Maybe you could argue down here, but it doesn't stay flat. It's changing at kind of around that point. So we just say that it's never constant. Our function is never constant, right? It's always heading decreasing, or it's turning out to be increasing. You could also say it's not applicable, right? Not applicable. Cool. Staying constant. Great. Let's see a couple more examples. Let's take a look at this one. All right, starting with increasing, I'm going to go through and label all the areas where we're biking uphill as we're going from left to right. Well, we're biking right here, uphill, so anywhere where you kind of had that positive slope, we turn around right there, so at that point we don't worry about biking downhill, 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 and we start biking uphill from these x values. On these x values, all of these points, we're starting to head uphill, like so. Then we start heading downhill, we hit this bottom, this trough, and we start heading uphill again, and we head uphill until we get to 4. Those are all of the x values for which we are biking up and hill if we're biking. Sweet. And so where are the areas we're biking downhill? That would be these areas here. Here, buddy. That's okay. He can get a cameo in. Yeah. Do you want to be on the video? You want to come down and be on the video? Okay. I'm already have the red pen up, so I might as well just do decreasing right now. I started the video. I already have the red pen up, so I might as well just do decreasing. Here's the problem. It's not one interval, it's 3, but they are all part of the, they were all spots where the function is decreasing. So we're going to use a special tool in our mathematical lunchbox here. I don't know why I said that, toolbox. You talk about each individual interval, and then you glue them together with something called a union. So there are 3 intervals. And we're going to kind of stick them together like so. Union represents kind of like an or inequality, like a holy matrimony. It's like they're married, except that's kind of weird because this is 3 people getting married, which, well, it's math. It doesn't have to make sense. Okay, let's go and do each interval individually. If you have more than one section, remember, join them with the holy mathematical matrimony or holy union there, right there. Okay, so you're going from -4 up to -2. That's our lower bound for this first interval. And then from 0, this is where we're decreasing from 0 to 2. And then the third one is from a little bit shorter, from 4 to 5. All right, and then in green, let's go ahead and do our increasing intervals. Where are we increasing? We're increasing from, man, I'm having fun. We're increasing from -5 to 4, from -2 to 0, and from 2 to 4. Okay? And lastly, where are we constant? Where are we constant? Are there any spots where it's flat? Nope. It's never constant. Always either increasing or decreasing. This is fun. Never stays at one value. All right. Here we go. All right. You guys can try this one. Pause the video. Give it a shot. See if you can get it. I'm going to start right now. Increasing. Let's go through, find my increasing. All right. Well, it's flat right here because this arrow is heading forever in that direction. So all the way from -infinity up to -4, it's flat. And then we start biking. So we're biking on flat. Then we're biking on downhill. And then we're biking on flat again. So where is it increasing? It's never increasing. Where is this decreasing? Okay, where is it decreasing? Well, anyway, we're biking downhill. We're biking downhill from here all the way up to 2. So we're biking downhill from -4 to 2. Now, do I use square brackets or parentheses here? For increasing, decreasing, it's hard to say what's happening at this point because it's constant on this side and it's decreasing on that side. So since it's kind of this bend in the curve, we're just going to use parentheses like so. You always just use parentheses if for increasing, decreasing. All right, and then, whoops, wrong color. Constant. Where is it constant? Well, there are 2 spots where it's constant. It's constant from -infinity all the way to -4. And it's flat or constant, 0 slope-ish, from 2 all the way to infinity. Fun, fun. All right, let's talk about a couple other things that we can use interval notation to describe. We're almost done. A function is said to be positive when it is above the x-axis. Okay, or it has positive y values. Okay, if it has positive y values, then it's above the x-axis, we say that the function is positive at that section. So here's what I mean. So like anything that looks like this. All of these points have positive y values, so we say in this case the function on this interval is positive. Okay, function is negative when it is below the x-axis. And when it's below the x-axis, it has negative y values. Okay? Negative y values. All right, fantastic. Hold on. Did it again. Here we go. Fix that. I'm OCD about my notes here. Okay, and what does that look like? Oh no, my cursor went away again. Gall darn it, let me pause it and fix it. All right, game time. When it's below the x-axis, and what does that look like? Below the x-axis looks like, you know, you have some line traveling down like this. It doesn't have to have negative slope. I should say, like, it could look like that. It could be positive slope. That's fine. It's below the x-axis, right? So we say that it's negative at that time. All right, and a function is an x-intercept when the graph crosses, you guys know this. Graph crosses the x-axis. Or it has the y value equal to 0. And a graph is a function has a y-intercept where it crosses the y-axis or has an x value of 0. So remember, crossing here, crossing there. Okay. Whoop, I have those backwards. Try that again, Slagle. X-axis is like this. Y-axis is like that. Sorry. Okay, cool. Okay, let's do a couple more little practice bits. Determine the intervals for the following functions where they are positive, negative, find the x-intercepts, and y-intercepts. We talked about can a function have more than one x and y? Okay. All right, let's go. Let's go, team. So let's start with positive. I'll do positive in blue. Where is our graph? Positive, positive. Where is it above the x-axis? So it's above the x-axis. From here all the way, where are the we're looking for the x values. We're looking for the x values when my function is above the x-axis. So it's above the x-axis from negative infinity all the way to negative 3. You want to make a cameo, buddy? Idaho? Oh boy. Okay. So we're doing some teaching online. You want to say hi to everybody? Oh, okay. He doesn't want to say hi. He's chilling. From negative infinity all the way to negative 3. Now, when it crosses the x-axis, is negative 3 included in above the x-axis? No, if it's on the x-axis, it's not above the x-axis. It can't be both. So this is actually a parenthesis here. And it's also above the x-axis over here, this direction. So there's an open circle here on both ends. Open circle at 3, right? So we have to put our union. Where is it positive? It's positive from negative infinity to negative 3. It's also positive from 1 up to infinity. Okay, switching colors. Where is this? Where is our function negative? It is negative. It's below the x-axis in this region here. That's where it's down, dip down below. And that is parenthesis because of that open circle, right? 0, if it's on the x-axis, like 1, crosses at 1, right? If it's on the x-axis, it's not part of my, it's not part of being negative. So that is from negative 3 all the way to 1, both with parentheses. And in, let's do it in purple. Let's talk about our x-intercepts. X-intercepts, we're going to list a bunch of points. We have 2 x-intercepts. It crosses at negative 3, 0, and it crosses at 1, 0. Those are our 2 x-intercepts. Our y-intercept, there is only one. It crosses only one time, and that is because it has to. That is at the point 0. All right, let's keep going. Switch into blue. Oh my goodness. Where is it positive? Where is it negative? and x and y intercepts. So where is it positive? Where is it above the x-axis? Above the x-axis here, above the x-axis here, here. And we're just talking about the ones we've already done. So those are the 3 spots where it's above the x-axis or positive. So let's list those, and we're going to join them together. So we'll say it's above the x-axis at, from -5 to -3, union from -1 to 1. Now notice these are not the same as increasing and decreasing. It's a similar strategy, but increasing and decreasing have different endpoints here, which is kind of interesting. 3 and 5. Cool. From 3 to 5, from -1 to 1, and we join all those with unions. You guys try and do the next one on your own if you haven't tried already. All right, negative, where is it? Negative spots we filled in here. Below the x-axis, here and here, we can say, all right, from -3 up to -1, union from 1 to 3. And again, no square brackets here because it can't be negative on where it crosses, right? It's on 0 there. Because those are our intercepts, which is a perfect segue. Go to our intercepts. We have lots of x-intercepts here. Lots of x-intercepts. Our x-intercepts are -5, 0, comma, -3, 0, comma, -1, 0, 1, 0, comma, 3, 0, and overkill 5, 0. Lots of x-intercepts. How many y-intercepts do we have? Well, only one, because it's a function, right? We can't have more than one. That would be 0, comma, 4. Okay, sweet. Last one. Last one. Let's do this. Positive, negative, x to y intercepts. I already got purple up. Let's do x and y intercepts first. The x-intercept in this case is also the y-intercept. They are the same point. But we say the x-intercept is 0, 0. The y-intercept is also 0, 0. Okay, where is this positive? It's a positive above the x-axis from -infinity up to 0, not including 0. It's below. It is below the x-axis, or negative, from 0 up to infinity. All right, that's it. Didn't shade everything there. Probably should. Keep it consistent. There's where it's negative. And this is where it's positive. Okay. Cool. Thanks for watching. It's been a heck of a video. I really appreciate you guys taking the time, check in and learn some math. Hopefully this was helpful. Hopefully you guys learned something, and we'll see you next time.